Good afternoon. So from today we will start second module of advanced material chemistry course. That is characterization techniques. So I am Dr. K.C. Barik from chemistry division. So I will cover next 6 lecture on characterization techniques. So today I will mainly cover basic concepts of of characterization techniques and its interaction of radiation. If you see any characterization techniques, whether it is an X-ray based or electron based or neutron based, so it's all that how does it that the interaction react to the matter? That is the basic principle. So that we will cover today. If you see any advanced material, so that advanced materials which are mainly they have some engineered properties. So you have to create some properties by using your specialized process and synthesis method. And when you go for this application of these materials, if you see that advanced materials application, you need to mainly 2 things. One is your structure, another is your morphology. Your structure has to be suited as to your application as well as morphology. And these two, that if you see the material properties, this material properties of that engineered material will depend upon the structure as well as the morphology. And then that to see those properties, especially the structure and morphology, you need characterization techniques. So the properties and performance of any material strongly depends upon the structure and morphology. So we will follow this various structural characterization as well as scattering different types of techniques to understand the material properties. So in this course we will mainly cover many advanced characterization techniques. That, for example, if you see that if I divide 2 parts, the characterization part, one is the structural analysis, another is your morphological study, or if you see the interface study. So mostly the structural techniques that will cover, one will be your diffraction based technique, and there is a scattering technique. When radiation fall on a material, it will be automatically it will scatter, or it will maybe absorb or some other phenomena may occur. Okay, but when the Bragg's law is satisfied, then only the diffraction will occur. So on the diffraction basis, we will mainly study these 3 techniques: that X-ray diffraction analysis, electron diffraction analysis, and neutron diffraction studies. In scattering, again we will see the X-ray scattering and your neutron scattering. These 2 scattering studies you will see. And when you come to morphology, we will mainly see either the interface technique we will use. For example, we can use XPS, that X-ray photoelectron spectroscopy, or X-ray absorption spectroscopy, just, or we can use secondary ion mass spectroscopy SIMS to study the what are the surface information, gather that information. If you go for imaging based technique, we will cover that only scanning electron microscope, transmission electron microscope, and atomic force microscope. With time permit, I will see this last one, but mostly I will cover X-ray technique like X-ray diffraction, X-ray fluorescence, then thin film XRD, then synchrotron XRD, single crystal XRD, and all those X-ray techniques that I will cover. Then even electron diffraction and neutron diffraction also. And similarly in the scattering, we will see 2 techniques. One is small angle X-ray scattering, another will be your small angle neutron scattering. These 2. So here these are X-ray scattering, here X-ray based technique, electron and scattering mainly X-ray and neutron, how they are complementary technique to each other, that we will study. And in this here in morphology, I will mainly focus these 6 techniques. So if you see all these techniques, that if you see that in that common phenomena, if you see that how does that radiation, that means a photon in case of X-ray or gamma ray, an electron and neutron, it interact with the matter. So that is the main thing that to decides how does that the properties you want to investigate, whether through a electron interaction, neutron interaction, or photon interaction. So this, if you see, the radiation interaction is somewhat close to that of how light interact with the matter. You all know that when light matter which meets with matter, there are 3 phenomena occurs. One is absorption, that that you can see the incoming beam here, and this beam can be absorbed with this material here, and then and completely absorbed or depositing energy to the material, or it can transmit it. It can be transmitted forward or backward. So those that will be your completely transmitted through this material. You will get transmission characteristic that interact and then transmitted through the material without either without affecting the material properties. That may be destructive interaction. It is not affecting, that will be non-destructive interaction. Another phenomenon that is scattering. The scattering that interact and scatter are deflected in different angle or in different direction by depositing the energy on the material. So this can be a photo emission or elastic scattering. So all those processes which takes place. So what you will see mainly these three phenomena occurring on a light-one matter. Another material phenomena that occurs, that is attenuation. That is nothing but combination of scattering and absorption. If you see the material, you will take 100% light is falling on this material. If 90% is absorbed, that attenuation coefficient, then you will see some light will be absorbed and the rest will be scattered. So the intensity of the light that will be attenuated will be I0, initial intensity, e to the power minus mu x. That mu is nothing but your fractional linear attenuation. You can also express in absorption coefficient, mass absorption coefficient by dividing density. So this means that initial incident ray and that final transmitted ray, after the attenuation process, you will see there is a change in the intensity of the light. So this is the common phenomena that is occurs in case of light matter meets with the matter. Similarly, when you see that radiation will meet with the matter, so mainly it may be a photon or an electron or a neutron. That interaction of all these photon, electron, neutrons, it follows the law of chance. That means if there is a material on its way, it will interact with there, or it can, after interaction, it may elastically pass through, or inelastically it can be scattered or transmitted. Those are observed, that phenomena will occur. So if you see photon, generally in a few interaction, mostly the exponentially it follows into the power minus mu x. That in case of photon, there will be few interaction is there, and photon interaction expressed in terms of cross section. When we discuss about neutron diffraction and neutron scattering, we'll discuss how this cross section is important. That means when a material fall on a material, when this photons interact, so it up to a certain zone that what is the cross sectional interaction, that the interaction volume will express in terms of cross section. And in case of electron, it experiences large number of interactions. And gradually it lose energy until they stop. And this expressed in terms of we'll discuss about interaction volume or electron range and stopping power, how the material strength of the material, what is the Z value of that particular material that can stop the electron to propagate inside it. So that we'll discuss later. And then we have a neutron, being that the neutron, if you see that there is a very small nucleus inside, then relation to the whole action, so neutron interaction is a very low probability. So most, if you see in any case, the electron interaction will be predominant than among the other three. If you see all the interaction, if you see whether it's a neutron, X-ray, electron, you can see this electron interaction. So there is two ways of interaction. Electronic interaction can be possible, as well as this electron scattering can be possible. Because for X-ray, there will be electromagnetic interaction, and X-ray being an electromagnetic wave, so it can be electromagnetic interaction, as well as X-ray scattering will take, because these are all the atoms in the lattice position. When you go to the X-rays or electron, so they will interact. So neutron being a magnetic moment, so there will be a nuclear interaction, as well as there will be a magnetic interaction is possible. So there will be a magnetic scattering in addition to the nuclear scattering. That is because of the magnetic scattering, so you will get lots of magnetic information, like whether it's antiferromagnetic, ferromagnetic, or paramagnetic. All those information you can also get from Newton scattering, Newton diffraction, where X-ray doesn't give magnetic information, whereas Newton diffraction you will get all those magnetic properties. Okay, so if you see, the whole atom can be interact with the incoming this radiation, or it can be a part of this that only nucleus itself can interact. So, or you can see the electron, the nucleus is here, and outer side, if you see the electron is moving here. So this electron, whether it's tightly bound or loosely bound electron, so those will interact with the this radiation or extranuclear space that surrounding the nucleus, whatever the space here, so that there is a Coulombic repulsion here. So because of that, so you can see how does this interaction takes place. So now, so coming into, we'll discuss each X-ray, neutron and electron individually. First, coming into X-ray, how does it interact with the metal? If you see, you have as far as I am concerned, that most of you have, most of you are PhD students or employee of PRC or any other institutes. So most of you come across these X-ray diffraction techniques or interaction of X-ray with metal. If you see that incident X-ray is here, it coming on a specimen. When it falls on the specimen, multiple phenomena occurs. So first thing, it can be absorption can occurs, and because of the absorption, you can see some heat. So material can be heated because of the X-ray. The energy can transfer from X-ray to the material, and it can be heated up because of the that background interaction that we discussed. Or you can generate that fluorescent X-ray, that incoming X-ray can be interact, and you can some fluorescent X-ray can coming out of the specimen, or that same X-rays can be scattered. That can be scattering, can be a coherent scattering or an incoherent scattering like Compton or modified scattering, but mostly loosely bound, charges are there. So that interacting with the X-ray beam, you will see incoherent scattering. And then you have if you see electron, when the X-ray interact with the specimen, then you can generate electrons. So that electron, that many two types of two electrons, or that one will be the constant electrons. So that from there you can study the Compton effect you can see, and then there is a photoelectron which mainly used in the this X-ray photoelectron spectroscopy at XPS, that is for identification of oxidation state, or coordination in the different environment that you will see using this the X-ray photoelectron spectroscopy. If there is that X-ray can also be, the chances can be transmitted to the material. The X-ray is very it can easily pass through any material. So because of very high penetration depth, it can be also transmitted. So another type of electron, that Auger electron, can be possible, like in photoelectron spectroscopy. The photoelectron, that Auger spectroscopy is there, that will cover the spectroscopy section. So all those type of interaction can be possible. So we'll go first to the coherent scattering. If you see, there is a coherent scattering when the energy of the incoming X-ray is very photon is substantially less. That that in center is the nucleus, and then electrons are bound to this with some particular binding energy. So each electron, that different K cell, L cell, M cell, each electron energy level has different binding energy. If the incoming X-ray has very less energy, so what will happen? There will be not much without any change. So what will happen? The binding energy, the electron radiation undergo change in direction without change in wavelength. That is the lambda I, the incident photon wavelength, the lambda f is the scattered photon wavelength. So wavelength will remain lambda I will be lambda f, but what you will see, so direction of propagation of that electron will change. So here, no electron, additional electron are ejected, no energy transfer will take place, since energy is very low, there will be no ionization process occurs. So this interaction mainly occurs when you have an X-ray energy about 15 to 30 keV in the range. But this low energy, though it doesn't give any information of the material property, but what will give, So this will be, your spectrum, will be looks very, you will give you very diffuse, like it will get lot of, background effect, that noise because of this coherent scattering. So there is a thermal diffusing scattering due to defects of the material, the defects. So because of the defects, this low energy X-ray can be scattered from the defects. Scattering due to slit, in-hole, binder or air scattering can occur. So all those things will contribute to the background effect. So it will neither, instead of giving any information of the material characteristic, it will give some background to the spectra. What you see noise, it will increase the noise. So you have to reduce this incoherence, that coherence, elastic scattering, so that you'll get very good. Your signal should be quite high. So then it's Compton scattering, that is incoherent scattering. In this case, Compton scattering occurs when incident X-ray photon deflected from the original part. Like if the incident photon is going here on the way, that X-ray photon or a gamma ray photon, and there is an electron is here, and upon impact the electron, what will happen? This loosely bound electron from the outer orbital, so they will scatter in different direction, and your incoming wavelength, that incident photon will propagate in some other direction. In this case, if the photon h nu is the incident energy, that and it's a scattered h nu dash. So kinetically here, that energy conversion, that momentum conversion, that conservation will occur in this case. So electron ejected from the outermost position, and due to the interaction, and energy changes depends on how the angle of this phi, that the angle of scattering, and not on the nature of the material or the medium through which it's propagating. An X-ray photon has less energy, it has longer wavelength, and then that's a less penetration than the incident photon. So what will happen? So it will go through to the electron, it just deviate its path and move into other direction. You can see here the kinetic energy, net energy will be h nu minus h nu dash, and there will be a change in lambda. So that will depends upon the cost to the depolarization effect that will be here. So if you see that there is no fixed phase relation among these incident and scattered wave, so they can propagate in any directions. And that cross section, if you see, with scattering from the electron, if there is cross section, electron is independent of your jet. But when you wait for atom, so it's directly proportional to the electron density. So it will depend upon the electron density to how much the Compton scattering will decide. So another one which is most important, that is the photoelectric effect. That is mainly, as you know, when X-ray photon coming, the incident photon eject an electron in the process. You can see this X-ray photon coming and falling on this core electron, and then this KSL core electron is knocked out. So it's come out, and there will be a vacancy, KSL vacancy created. So the electron is coming out, which is a photoelectron. And that vacancy exists with the removal of the electron, and that's one or more characteristic. That's once this photoelectron comes out, and then what will happen? The higher orbital energy, they will jump to this place, and because of this, what you will see some characteristic, emission characteristic X-rays are being produced. And these characteristic X-ray are depending upon K alpha, L alpha, M alpha, they are of different energies. You can easily identify from which orbital is coming, and then you can find out that corresponding oxidation state by using this X-ray, this photoelectric effect that you can use for that in the X-ray analysis, photoelectron study, or you can see the OJ emission process. All those things can be occurring in case of photoelectric. But if you see the energy of the photoelectron with the incident photon minus that binding energy, as I earlier discussed, that each electron here, they are bound to the nucleus with some binding energy. So once this electron is coming out, so it has to overcome that binding energy. So what will happen that the photoelectron energy will be incident photon minus binding energy. So what will happen? The photoelectric effect is mainly predominant for low energy photons, but higher than the binding energy. It should have higher than the binding energy of the electron, but mostly low energy photons. It gives photoelectric effect, and high jet, high atomic number. That will so predominant photoelectric effect. You see the probability of interaction here proportional to check to the power 4, that's atomic number, to the e to the power 3. So inverse proportional to e to the power 3. So in addition to this photoelectric effect, There is another phenomena occurs when X-ray, gamma ray or X-ray photon interact with the material that is your pair production. So pair production means the X-ray photon is coming here. This is the X-ray photon. Then X-ray photon pass near to this is the nucleus here, and near to the nucleus, what will happen? So there, the photon converted into two particles, which will be a generated electron E minus and a positron E plus. So that means to create these two particles, that you need the minimum energy will be 1.2 MeV, the minimum energy requirement for this. Whatever the excess energy here, that is given to the particle as a kinetic energy. Because of that, this they will move far away. So the mostly that is this undergoes a typical charge particle interaction by losing energy during each interaction. So as pair production occurs at the field of nucleus, the interaction is approximately proportional to Z square. So mostly to pair production to occur, you should have minimum energy of 1.2 MeV. In pair production, the X-ray photon or gamma ray photon is divided into two units. One will be electron or one is positron. That you will get. Similarly, sometimes electron and positron they meet together to give you X-ray photon or a gamma ray photon. Is possible. That's called pair production. So mostly, if you see here in this graph mass attenuation coefficient with photon energy, you can see as low energy, mostly your photoelectric effect is predominant here in low energy, but in high energy, that is more than 1.2 MeV, there it will be 0 to MeV. That pair production will occur. And in between these two, you will see mostly Compton effect that will be given to the background noise mostly. So if you see here, overall, the spectra will be, most of the material, the spectra will be like this. Only thing is that the energy position will shift depending upon the Z of the material, or how it this distribution of the, depending upon the basis material distribution, types of interaction, which one is dominant, and what is the material property that we decide. So in general, at low energy, photoelectric effect, at high energy of pair production, and Compton effect will be done. Another type of interaction that cause damage to the material system, that is the photointegration, in a direct interaction of energetic photon, very, very high energetic photons, and observed nuclei. So after being excited by the photon, you will see, the gamma proton neutron or gamma neutron reaction. So proton or neutron will eliminate from the material. So for this, the minimum threshold energy of high energy, like 8.5 MeV, are all nuclei to occur. So at high energy, you are able to see. In case of deuterium, you can see that 2.2 MeV is possible at barium at 1.67. So you know that here it's occur, but mostly in general you need much high energy to see the photo disintegration process. So when that we discuss when X-ray interact with the material, one is your Compton effect, elastic scattering, then you have a photoelectric effect, that's photoelectron generation, and then there is possible of pair production or photo disintegration. So these 4-5 things occurs when your X-ray interact with the material. Similarly, when electron interact with the material, various phenomena occurs. So if you see, the electron is an elementary particle that carrying negative charge. So the rest mass of the electron is 9.1 10 to the minus 3 at 31 kg, and charge is about 1.6 10 to the 19 coulomb. So this here, the asserted electron, so the electron is moving in a particular path. So first the electron is generated from the harmonic emission or field emission, but that is from there it go through different magnetic lenses in case of scanning electron microscope or transmission electron microscope. While passing through these magnetic lenses, it's that electron velocity accelerated. So because the accelerated, your kinetic energy is getting more and more increases. So because of that, your accelerated electron that will act as both particle as well as wave. That means de Broglie equation. It follows, and this is the interaction where electron beam can be either coherent, it can be coherent, all can be in a phase. So you can get a summation of all these, or they can be incoherent, they can cancel out each other. So if you see that the incident electron, it falls on a material, if you have a specimen here on the specimen, if your electron beam falls, So there is a probability that the electron can be, absorbed and can generate a secondary electron. So you can remove a secondary electron. That means the incoming electron can absorb in the material and it knock out a secondary electron, or it can be produced. X-rays can be produced that and then you can also get a backscatter electron. That same electron, if very close to the nucleus, they can get back as a backscatter electron. So as you know that backscatter electron and secondary electron, these two are the commonly used in scanning electron microscope. If you see the scanning electron microscope, SCM mostly use backscatter electron or secondary electron, depending upon the topographic image you want, or you want some other information, you can use either backscatter or secondary electron. And this X-ray that produced by the electron absorption, as you know that EDAX, EDX or EDX, energy dispersive X-ray spectroscopy. So EDAX analysis you can use to do composition analysis. You want to see what is the element constituent, whether it's manganese, cobalt, nickel, so that M alpha, K alpha, or K beta, you can able to see by the EDAX analysis chemical composition. And there will be a inelastic scattering electron that will give you mostly background effect. And if the electron is transmitted to this direct beam transmitted, that transmitted electron beam is used in TEM, transmission electron microscopy. So if you see all the phenomena of that SEM, TEM based on how electron interact with the matter, and then there will be elastic scattering is possible. In addition to that, there is a Auger electron can also produce. So Auger electron is a 3-electron process that we'll discuss later. So this Auger electron that you can use in Auger electron spectroscopy, AES. So overall, the all characterization techniques that we material, inorganic material characterization technique we do to SEM, TEM, AES, so that based on the interaction of the electron with the metal. If you see, when it interacts, there is one possibility, there is an elastic collision. Elastic collision means there is no energy loss, no energy transfer from electron. If the electron is coming here, this is the sample, so it will interact without losing an energy. So there will be no change in energy. Electron penetrating the electron penetrating into the electron cloud of an atom that is attracted by positive Coulombic interaction, and here the elastic interaction deflects the electron being new trajectory. You will see it's coming electron, it enters the material and then it ejects out. So here E and E, the incoming electron energy and this energy are all same. But if you see, these are you can see the electron is coming here and making an angle, they are going. So they are scattered electron. But if the electron is coming very close to the nucleus, so then electron that it can be attracted towards each and can be go like this, that is the backscatter electron. So a strong elastic scatterer very near to the nucleus may result a beam of electron leaving specimen by backscattering. That is called your backscattered electrons. So then there is a probability, if you see that elastic interaction that mainly proportional to the atomic number Z square and decreases as E by energy square 1 by E square, that electron energy decreases 1 by E square. And in addition to elastic, there is a possible inelastic collision, that is, as you know, in TM there is a electron energy loss spectroscopy, EELS, that will discuss electron energy loss spectroscopy in the TM class. So there is that inelastic, that collision, that energy loss used to determine the oxidation number as well as coordination number in case of ES. So here energy is transferred from the incident electron to the sample, thus affect the interaction energy. You can see is the incoming electron energy E, and then after interaction is E minus W. So W energy it is losing with after interacting with the material. So this energy loss happens gradually with the distance is traveled. It is dominant energy loss mechanism in case of electron. The elastic interaction collision is the dominant energy loss mechanism. The interaction produces excitation and ionization can be possible in case of this. So in elastic collision, electrons are produced, additional electron. As I discussed, that one is your secondary electron can be produced, but the backscattered case, the same electron is coming back. In case of secondary electron, you can see here the incident that the electron beam is coming here, and because the incident electron beam, it's knock out the electron, one electron from here. So that is your second electron. That second electron can produce, so that will be used in SCM, and then it can produce X-ray photons, the gamma ray photons or X-rays. It can produce, and it can produce Auger electron, all those things. So high energy electron of incident beam removes electron energy. You know, if you see the X-ray photoelectron spectroscopy, we use aluminum K alpha or magnesium K alpha. They are used. So they are high energy electrons. So in pulse, it moves out X-ray photoelectrons or Auger electron in that case. Okay. So hole in the inner cell will be filled by the electron, the outer cell here. There is another electron here. So because of this hole, it can be filled, and that will be used in case of causing X-ray or Auger electron emission. So that this characteristic X-ray that we will see, that will be different for different material, and we use in X-ray photoelectron spectroscopy. So in addition to this elastic and inelastic emission, there is a possible background emission, that is Bremsstrahlung emission. So electron emits Bremsstrahlung due to the acceleration caused by the electrostatic field of atom. When electron is moving through the close to the nucleus, so there will be electrostatic field of atoms there. So because of that, in the due to the acceleration, so it will continuously lose some energy. So that electron an electron with energy E generate a photon of energy W here. You can see this photon is generated. Because of that, it will give some background to the system. And then there is a position annihilation, that is here that if you have an electron is there, and that electron and a electron and a positron, which will be positron, they can come closer, you will get a gamma ray photon because of positron annihilation. So positron penetrating a medium can annihilate with electrons in the medium, and by emission of you see mostly 2 photon, 2 gamma, or 2 photons in the see here. So if you see that whether it's a collision interaction of electron for collision with the nature, either it is elastic or inelastic, it depends upon the particular interaction volume. That particular interaction volume, that the 3D space in which the electron beam can be migrated. If we see here, this is a specimen here, and inside the specimen, the electron beam is coming here. You can see the electron beam is going like this is going inside. So this is the area up to what the electron beam is penetrating. Here, this is the volume in the specimen. It's better to say the volume in the specimen to which the electron beam is, interacting. So that is nothing but that is called interaction volume. The region generated because of this interaction, that the incident electron beam over 3-dimensional region inside the material, you will get a interaction volume. Or simply you can say it's a electron range. That means up to what range that electron can penetrate or migrate, that you can also express in electron range. So electron range is as simple as a value that is useful. If you see the high Z material and low Z material, so how the electron density that it changes on that depending upon the Z, and accordingly the electron range will change. If you see here that you can see in low energy photon is coming to a low Z material. A low Z material means, for example, you can take a silicon, magnesium here, or here you can take silicon, here you can take tungsten or some high Z material, gold, like this type of high Z material. If you see the low kV, you will see it will go away, it will form a propagate deep inside. But in case of high Z material, it will just penetrate it. The volume will be longitudinally, horizontally it will be a large volume, but here vertically penetration depth will be high. But in case of high kV, you can able to see it can go much high interaction volume, but here in case of high Z, that because of the high density of the slightly stop and you get a smaller interaction volume. Briefly, if you see that this electron range R will be depend upon that Z value, atomic number of that element, and get the energy of the incident beam, or the energy of the incident beam, and then that Z value to see the penetration depth or electron range you are able to see by using this interaction value. As you know that if you see in TM, for example, if you see a core cell structure, most of you see like from a high-jet material, for example, this is your nickel nanoparticle. On nickel, you have a coated a silicon coating, SiO2 coating. So you will able to always you will see this is much darker and this is lighter. Because of that, it's a high-jet material. So that's a, transmission of electron will be less in that case. Your transmission is much higher. So those type of all those it depends upon the interaction volume or electron range, how does the interaction. So what we discuss in case of this interaction volume, if you see that if you see here that this is the incident beam, this incident beam is coming here, and after interacting, you can divide into different zone that the whole interaction volume. On the top level, within 1 nanometer here, you can see you mostly will produce J electrons or second electron. So second electron is just coming from the top surface that you will see. A little deeper, you will be able to see the backscatter electron. So this electron will go inside and then it will come out. That will be backscatter electron. Here up to 500 micron. In that range, you will consider this backscatter electron. And little more if you see go to 1 to 3 micron, you will be able to see the characteristic X-ray. So characteristic X-ray emission will come here in this range. So that will be useful. And then if you go much beyond this, like 1 to 4 micron, there mainly it gives when constant harm, that is the background radiation. You will see the background radiation here. And then beyond that, you can also see some patholuminescence. If it's transmitted through this, then you have a transmission electron beam. So if you see that the second electron is coming from the top surface, so that second electron you will use in SCM. So you will use in SCM, and if you backscatter electron, that again you can use in SCM. These two, and if the X-ray is coming, there is background X-ray, and from here the characteristic X-ray that is coming in 1 to 3 micron, that you use in EDAX, TM or SCM EDAX analysis, which is mainly for the compositional analysis, you can see that the electron is transmitted, then you will be able to see the TM, whether it's elastic scattering and inelastic scattering. As I told, the inelastic scattering, you have a electron energy loss spectroscopy, EELS, electron energy loss spectroscopy. So there you will be able to find out mostly the oxidation state and coordination number. So that we will discuss later on in TM classes. So if you see the backscatter electron, the coefficient of the backscatter electron will depend upon total number of current passed through the material and how much backscattered electron coming out. That will be the coefficient. If it depends upon that, if it's a perpendicular 90-degree angle, the backscatter will be much higher. So it depends upon this phi value, that is tilt, is called tilt angle, up to what angle that incident beam is coming. So depending upon that, you will be able to see the backscatter coefficient, how much you can generate, and this is monotopical increase. If jet value increases, the high jet material, the probability of getting backscatter electron is much high. So that will more use in atomic number contrast image, and also you can use them topographic image by using this tilt angle facility. So mostly backscattered electron is used for the atomic number contrast in case of SCM studies that use. Another is secondary electron. The secondary electron means that it is a bound electron which is loosely bound on the outer orbital. So when the incident electron comes, so that will knock out the electron from the core material, from the inside the original material. So that will be secondary electron. So here again, the coefficient depends upon number of secondary electron coming out by total number of the current passes. And in addition to secondary electron, you can also possible a SE2, that first secondary electron will generate an SE1. That during this process, you can also get another electron is possible. So overall, if you see, the emission of second electron is very sensitive to the condition of surface, because since it's coming from the top surface, depending upon the surface, the low kinetic energy, how much energy penetration that incoming electron is penetrating. So those are the material characteristics that will decide whether the second electron is coming out or not. So far I discussed mostly that this interaction of electron and X-ray, which nature. So then we'll go to the neutron interaction. So we'll take a short break here for 3 to 4 minutes, and then we'll discuss the next part. If there is any question, you can raise in chat box, or you can also raise question here. So now we discuss about interaction of neutrons with matter. So so far we saw that when X-ray or electron they interact with a matter, in both case there will be some loss of elastic or inelastic in case of scattering there in X-ray, in case of interaction, in case of neutron. Similarly, in case of electron, similarly in case of neutron, it also interact with the matter. So if you see this neutron was, as you all know that Neutron Chadwick was discovered the neutron and he used Nobel Prize in the year 1935. The first that beryllium with helium, if you interact, you will get one carbon and a neutron. So the neutron has mass of 2000 times of electron. Its mass is about 1.67 to 10 to the minus 27 kg, and it has a nuclear magneton. It has a magnetic momentum like electron has a electromagnetic moment that is mu b, Bohr magneton. Similarly, in case of nuclear, they have a nuclear magnetron, and it's indirectly ionizing radiation. It's a ionizing radiation that indirectly. And then if you see the properties of neutron, so neutron is mostly electrically neutral, so they can. Because if you see the depth of penetration, it's much higher in case of neutron, and in a microscopically it's a magnetic, and in the wavelength in the range of angstrom order, and energy of milli-electron volt, and can show its motion. That means that it gives the information about structure that means very small wavelength. If you see, for example, copper K alpha that we use in X-ray, the wavelength is lambda is equal to K 1.5405 angstrom. So being a very smooth, low wavelength, you will be able to see the structure information in case of X-ray diffraction analysis. So similarly, this neutron wavelength in the angstrom region. So because of that, that will give you structural information, and that energy in the milli-electron volts can show motion. So because of that, you will get both structure and dynamic information from electron neutron scattering studies. Okay. So if you see the type of neutron, so neutron, mainly there is one thermal neutron, that are slow neutron, the energy is less than 0.05 electron volt. Then you have a intermediate energy neutron, that energy is in between 0.5 electron volt to 10 keV. And then there is a fast neutron, energy is much higher than 10 keV. Like electron, neutron also follow de Broglie relationship. And if you see from this neutron, the how that so I'll discuss a little bit basic about neutrons before going to the details. So if you see the neutron, mostly that the spontaneous source, that fission reaction, the source of neutron. So neutron you can produce by a spontaneous fission reaction, whereas uranium, for example, uranium will be, you can by the slow neutron interaction with the krypton and beryllium, you can get 2 to 3 neutron from this. So that's one will be your spontaneous fission reaction, and then there is a photonuclear reaction, that is nothing but this is your fission reaction, first one, and then this will be your mu n gamma n reaction. So you can see, you can apply gamma energy and you can get neutron. That is another possibility. And third is neutron generator. You can use different spallation source, high energy sources, either by laser driven, or we can high energy laser can knock out electrons. So you can neutron generator can be seen. So mostly the spontaneous fission reaction that occurs in a research reactor following the chain reaction, that so you get 1 neutron per fission and our energy of 180 MeV per neutron. And in case of spallation or laser driven, so here there is no chain reaction. So here pulse operation and you get about 30 neutron per photon you will able to get. So in case of spallation, you can see the breakout here. In case of fission source, in case of spallation, you can see here when that because of this high energy laser driven or some high energy, you can able to get nuclear cascade, and from there you can able to get that neutron you can able. So mostly neutron you can produce by spallation source or by research reactor. You see that how that fluxes the brightness, you can see brightness of the X-ray and neutron to compare. So as I told in the beginning, the X-ray and neutron gives complementary information to each other. You can see it says the neutron, that flux is of about 10 to the power 11 order, and that of brightness is 10 to the 15 order of second per meter square per sphere. And in case of, you can see that this the X-ray, that the X-ray that produce in single crystal rotating anode, in case of single crystal XRD, or in the X-ray produced in this synchrotron. This is synchrotron. You can able to see the order is that brightness is much higher, and similarly flux is of order of 10 to the power 24. So that even at low amount of X-ray and very low quantity of sample, you will be able to see the structural information in case of using that high energy synchrotron radiation source. But in neutron energy is somewhat brightness is 10 to the 5, 15, and flux is under 11. Because of this flux is very less compared to X-ray, that what you see, you need longer experimental period, that longer time period to get information, much information about the neutron characteristics, neutron characteristics. So,
Sir, excuse me, sir.
Yes. Tell me.
Sir, two slides before this, you had mentioned they're written randomly sensitive, so they can see hydrogen atom.
Randomly sensitive, yeah. Okay,
Yeah, what
that
do we mean by randomly sensitive?
that I missed actually. If you see the neutron, so neutron mostly in X-ray, that those are mainly high energy, like the high jet material. If you see, most of the inorganic system able to use X-ray to get information, but hydrogen is a light element. Okay, so there you can't use that X-ray, so you have to use neutron. In case of neutron, neutron can interact with the hydrogen, and as you know, the hydrogen and the deuterium. So there, the neutron can interact with hydrogen or carbon, a small, molecule, small atomic number systems. So there we'll able to get information about those structure. For example, you have a surfactant molecule, and that those consist of, for example, sodium rhodecyl sulfate or CETA. So those are simple carbon hydrogen constituent. So there you will not get any X-ray diffraction pattern or X-ray information. But if you see the small angle neutron scattering, you can easily, randomly sensitize that those hydrogen atoms can be give you information about the position. All those things can get how that interaction that there is a two. I'll discuss when the neutron scattering study. I will discuss the small angle neutron scattering. There I will discuss. In case of X-ray electron density, that is important. But in case of neutron, there is a scattering length. Scattering length means that I will discuss that how much scattering capability of the particular element or particular material. So that scattering length will depend upon the hydrogen, and its a counterpart is a deuterium. So deuterium, there will be two numbers that will get these two photons. So because of that difference, one will be a positive, another is negative. So because of that, we will able to see that neutron in detail information. So you can right now you can just remember that it will be easily sensitive, give information about hydrogen containing atoms, which X-ray could not decide. So that we will discuss later on when we will come to that class. We will discuss. Okay. So this we will discuss. So then this neutron interact with the material like the X-ray and this electron. It can be interact with the elastic scattering. It can be inelastic scattering, or there can be absorption or fission. If you see here, the elastic scattering, that same NN interaction. Inelastic NN, there is some energy loss can occur. An absorption or a capture, neutron capture reaction can occur. So because of capture, this neutron can capture, you can give some gamma ray, N gamma reaction is possible, and it can go through a spontaneous fission process. So that is no charge here being no charge interact with the nucleus. That is, this electron and X-ray, those will be very difficult to come closer to the nucleus. Being no charge, neutron can go closer to the nucleus and then interact directly with the nucleus. You can see the nuclear radius 10 to the minus 13 centimeter in that short range interaction we are able to see here because of small size nucleus in relation to the atom. So neutron probability, interaction probability is very, very less compared to that of X-ray and your electron. But this interact with both electron by magnetic moment. As I told, like electron, neutron has a magnetic moment, so it will give you, information about magnetic properties. So yeah, so it will go through neutron high penetration depth I discussed, and then neutrons captured by nuclei, not electrons. Like X-ray, this electron they are scattering from the electron orbital, but here it can scatter from the nucleus only. There is possible electric scattering that is just the same neutron will come out here, and the resonance scattering electron. So there will be no significant change. In inelastic, it will go to an excited state, and then same electron come out. And radiative capture, as I told, that neutron can be captured. So once the neutron will be captured, we'll get a metastable excited state, unstable state. From there, that again jet flows will come out and gamma will come out. Or you can produce photon, deuterium, helium, that alpha particle. You can go to the fission reaction. All these possible in case of neutron interaction. And then if you see the neutron interaction, one important is neutron capture. So here, neutron captured by the nucleus of the observing material. You can see the new sodium 23, this neutron absorbed, and it will go to sodium 24, and gamma ray will come out. So it can form a compound nucleus that is possible. Here it is that the N gamma is possible, N E possible, N alpha, N P, depending upon what is emitting. So you can different reaction is possible. When gamma ray is coming out, that is called radiative capture. Gamma being the radiative in nature, you call it radiative capture. And probability is capture inversely proportional to the energy of the neutron. Depending on the slow neutron, the capture will be high. So low energy, slow neutron have highest probability of capture. That means your interaction will be high in that case. Okay. So then, if you come the neutron capture, some of the example here I have just shown here. I will not discuss detail. So even hydrogen can capture neutron, will give deuterium and gamma can come out. Similarly, neutron with cadmium, that cadmium 114 and gamma ray can be radiative capture. And you can emit some charged particles. A neutron with boron and lithium and helium can come out. You know, this is the boron neutron BNCT, boron neutron capture therapy. That BNCT is generally used for cancer treatment. So there is that this helium is alpha particles coming out for that used for cancer treatment. And similarly, boron that we see now with nitrogen, the carbon 14 and proton can come out. So it's a charged particle emission is possible. Radiative captures are possible. So this is important mainly for neutron dosimetry studies. And another slow neutron can interact with the hijacked like uranium 235. You can go a fission product, and 2 to 3 neutron can be produced. So mean number of neutron will be around 2.5. So the absorption of neutron produce a compound nucleus. Then compound nucleus is highly unstable. That if it cross the critical energy of the fission, that delta M it crossed, then you'll able to the fission product will be able to see. So another thing is that that the interaction of the slow neutron that I discussed, the fast neutron, the energy is less than 10 MeV. That there is electric scattering will be possible. And neutron interact with the particle of same mass, like that both same mass. Like one neutron, another mass is coming. For example, like water or wax, those containing mostly hydrogen element. So it will interact with that. So there will be same mass. It's a billiard ball type interaction. So it will give you, after collide nucleus, neutron deflected, it's with the position, you will able to get a recoiling nucleus in this case. So total energy will be conserved in this case. And in case of inelastic scattering, for example, that is a much higher jet mass, the neutron is interacting with the iron, cobalt, or stronger material. So analogy of ping pong ball striking a bowling ball. So one small and one big one, they interacting. So in this case, energy transport to the target nucleus. So energy incoming neutron after interacting with here, so energy will be transmitted and the neutron re-emitted here, and then neutron re-emitted with lesser energy. So here the nucleus left excited state and relaxing emitting neutron as a gamma rays or charged particle will come out. So total energy here is to be conserved and not significant, the inelastic scattering which occurs predominantly in high Z materials and not significant on tissue growth dependent. Like if you see the body tissue dependent, the first neutron doesn't affect much, but is that it's mostly high Z material that you see. So if the first neutron, in case of nuclear reactor, that the chain reaction to sustain, so the first neutron, then you go to thermal neutron, slowly you can go to thermal neutron, 1 MeV neutron, you can interact with nucleus, lose some energy, 100 MeV to 10 keV, and finally, at the very that thermal neutron, you can produce 0.025 electron volt energy. So the first neutron, thermal neutron, then neutron capture occurs in this case of neutron interaction. The whole this how does the neutron interact with the material? It depends upon neutron cross section. So neutron cross section, the probability of interaction of a neutron with a given material is expressed is a neutron cross section. That unit is barn, that generally one barn is 10 to the power minus 24 centimeters square, that you can see here the number of scattered neutron per second by incident neutron flux that will express. It depends upon nuclide as well as neutron energy, and total cross section will be how much neutron is scattered, how much captured, and then how much is fission product. So summation of these three will give you a total neutron cross section. So if you take the macroscopic scale, if you see that the n number of Avogadro number of atoms, the total is n0 into sigma total. So to increase the reaction probability, so you need moderator neutrons to lower down the thermal velocity. Once you have slow neutron, your interaction will be high, and you will be able to get this higher cross section. Mostly that graphite and heavy water, they are used as neutron moderators. So if you see, the neutron interaction also follows like X-ray photon. So you see the I will be intensity, that I0 initially e to the power minus mu x, it depend on, that in case of this mu, that will be nothing but your this attenuation length will be characterized here. Next, here a term is coming, that scattering length, the neutron depends on the isotopic isotope independent. As you know that X-ray, if you see, I just discuss a simple example. In XRD, this is an XRD, this is a neutron diffraction. In XRD, most of you might have seen that low angle peaks are smaller, low angle peaks are quite high intensity. Then as you angle increase, 2 theta value increases, your peak intensity decreases. Intensity versus 2 theta, but the neutron diffraction intensity versus 2 theta, these peaks are random. So they are random. They doesn't follow that with 2 theta value, the intensity that it doesn't linearly decrease like X-ray, because in X-ray it's electron dependence. An electron dependence based that depends on sine theta by lambda, that wavelength sine theta. I will discuss a little later when in X-ray diffraction how that scattering factor sine theta by lambda is depend upon scattering factor, electron scattering, but in neutron that scattering length is independent of that Z value. So even hydrogen or a zirconia, if you compare that scattering length is they are not depend upon the Z value. Because of that, this peak intensity are random. In case of X-ray, the peak intensity are linearly decreases. That we will detail will discuss. So far what I discussed that mainly so I have discussed how does the material interact with the X-rays, neutrons and protons, and because of this interaction that 1 minute. Just see, so, so far we discussed that how does that neutron and X-rays and this electron interact with the matter, and then I have just given a basic background about that how this X-ray, all those things interact with the matter, because all these interactions decide the characterization techniques. Before going to the characterization techniques, I thought I will give a clear idea about how does this interaction occurs, and then now coming into the first part, that the X-ray and its properties. So I will discuss first X-ray diffraction techniques or X-ray scattering techniques. So before we go into that, so if you see the X-rays and its properties that you all of you know. Yeah. So if you see that X-rays and properties. So X-ray discovered in 1895 by Röntgen, and when he discovered, that time he doesn't know that exact name, so he termed as X. That X stands for unknown. So when he was doing some experiment, he observed that new type of radiation, possibly due to interaction with electron. That time he thought the electron with the glass wall of the tube that could be detected outside the tube. So that the X-ray he defined as a weightless package of pure energy with no electrical charges. As you know that X-ray doesn't have any charge, and travel in a wave along the straight line with the specific frequency and speed. So that was the X-ray initially that we thought. And if you see the X-ray, that the X-ray has both physical and chemical as well as biological property, or some physico-chemical properties. You can see here X-ray stands in this is the wavelength of the range of 10 to the minus 10 to minus 11. Here that X-ray which has this region, that the electromagnetic series. If you see the physical properties, X-ray belongs to the family of electromagnetic radiation, that wavelength of 10 angstrom to 0.01 angstrom in that range, and travel at the speed of light in vacuum, and it's invisible to us. You can't see them. They can be reflected, refracted, or deflected by magnetic and electric field, and as they don't possess any charges. Okay, so they are pure energy with no mass and transfer energy in the form of quanta, that is called photon. So they can penetrate various objects, and its penetration depth depends on its intensity and the wavelength. And if you see, these are the physical properties. If you see the chemical property, X-ray induced color changes of several materials. If you see methyl blue, it can be bleached out. Like for apple green color of sodium pentacyano-side will turn to dark green, or so on. You see different chemical changes occurs. So X-ray can also destroy fermenting power of enzymes, and can affect the photographic paper thin film in the same way as visible light. So X-ray excites biological material which enable them to part of chemical reaction which are otherwise doesn't undergo. That is because through X-ray you can mediate some experiment also. They are transmitted through healthy tissue but not absorbed by the bone. Because of that, we use that X-ray for the medical diagnosis. You can easily, the bones are made up of calcium in the hijack, so there it can't be absorbed by the bones. So you'll get a image, and then it will transmit it to the tissue. So if you see how we can produce the X-ray, so the X-ray can be produced by conversion of kinetic energy of an electron into electromagnetic radiation. You can see this is an X-ray tube. In the X-ray tube, you have this filament here. From here is the tungsten filament. If you heat it at high voltage, what will happen? From here, electron will come out. Then the electron will fall on the copper anode. This is a copper anode. Generally, we use in X-ray production. So copper or molybdenum used as an anode. So this from the copper anode, after falling of the electron, high energetic electron, so it will come out, some X-ray will come out. So we'll able to produce the X-ray, and whole thing will be encapsulated in a high vacuum. So mainly produced by striking a high energy electron beam on a metal target. Your metal target is your copper. On the copper target, you are by thermonic emission, you are creating electron from the tungsten filament, and then that electron is falling on the copper anode to give you X-ray. So if you see the different parts it has a X-ray tube that requires the electron source. This is the electron source tungsten filament. Then if you need a potential here, the electron which produced here, it has to be high acceleration. That means high kinetic energy. So for that you need a acceleration potential, positive potential that you need here, the high potential. Then is the target source to generate the X-ray. So major component, that means you have a cathode, that is electron source, and anode, that is the copper target for acceleration potential, and a targeting device, that is rotor, or the whole thing is inside a vacuum. So anode is target electrode and it's maintained a high positive potential difference with respect to cathode. Because of that, this electron beam fall on that cathode, this anode, and it produce X-ray. So if you see the electrons released from the cathode are accelerated here. I already discussed this. When they fall on the anode, energy loss to the electron takes place by scattering an excitation process to produce X-ray. So if you see, the intensity of electron beam decide what is the energy or what is the intensity of X-ray radiation. So whatever the X-ray radiation is coming out, that intensity will decide by the electron beam energy. And then if you see the kinetic energy, 99% kinetic energy is converted to heat. Only 0.5 to 1% of the kinetic energy will convert to X-ray. So because of that, this heat generation here, so 99% kinetic energy lose, only very less electron energy will use. Yeah. Yes. So if you see the projectile electron is coming here, that electron released from cathode interact to the outer cell. So the outer cell, there are many electrons. So because of this interaction, the electron were not of the target atom, but don't transfer its energy. The X-ray is coming out, so that the projectile electron from the cathode interact with the outer cell of the electron target atom, but don't transfer energy for ionization of the outer cell electron. So outer cell energy are simply raised. So what happened when X-ray is coming, projectile electron is coming here. So instead of transferring its energy, it don't transfer energy for ionization. It just interact. So because of this interaction, outer cell electron is simply raised to an excited state, and outer cell electron immediately back to the normal energy level by emission of infrared. IR emission is there, and this IR emission is the cause of that. And then the heat production. So because of that heat production, 99% intensity will be X-ray, that kinetic energy loss, only about 1% used for the characteristic X-ray production. So in case of when that X-ray production, there are two things occur. One is characteristic X-ray radiation, another is your this background radiation, that Bremsstrahlham radiation is possible. So X-ray produce Bremsstrahlham radiation as well as characteristic radiation. So projectile electron, mainly this characteristic X-ray radiation that is coming out, that we use for in case of XRD, or you use that characteristic X-ray. But this Bremsstrahlham mainly give you the background. So projectile electron interact with the inner cell, the target electron. You can see here that this incident electron beam is coming here. These are the incident electron beam is coming here. It's falling in the core electron. Here is the electron here. Then that electron, the projectile is coming out. In this process, what has happened is knocking out one electron from here. So because of that, the higher orbital is getting vacant. From there, it's migrate an electron to the lower state, and then you'll be able to see some characteristics. It's coming from K cell, it's K alpha, L cell, it's L alpha or L beta, from M cell, it's M alpha or L beta. So you produce this X-ray, characteristic X-ray, then that characteristic X-ray will use you. So if you see briefly, each electron in the target atom has a binding energy. So they are bound with some energy. So the incoming electron beam has higher binding energy, then like a photoelectronic field knockout, and the on field that higher orbital electron fall this empty orbital, you will able to see the X-ray is produced with energy equal to the difference, the energy from coming to here, so how much energy it lose, so that energy is your characteristic X-ray energy that you see. So if you So if you see here, if it is a K cell, L cell, M cell, you see from K cell, K alpha n equal to 2 L cell, from L cell to K cell is coming, this will be called, K alpha. This one will be K alpha. Similarly, from M cell, it's coming to K cell, or it's a guy, N cell is coming, that there will be K beta and a K gamma will be produced. Similarly, in case of L alpha, is N to L cell, or N to L cell is L beta and L gamma, or similarly for M cell. So these are different, this K alpha, K beta, K gamma, they are of different energy. For example, if you see copper K alpha, there is 1.5465, and K beta is 1.54, this is 0.5, and this is different. So you will get, the all K alpha, K beta, K gamma, they are of different energy. So you can, depending upon that, you can identify the element in case of, the SCM or TM EDAX analysis, or you can use them, this K alpha mostly used in, copper K alpha for X-ray diffraction studies. And then depending that this, you can all, that energy released, you can calculate from which orbital it's coming. And this is the diagram that I am showing, that how K beta and K gamma is produced from this. And then if you see that so characteristic X-ray, where K cell, you can see here energy of the K cell is 16, for tungsten is 69.5 electron volt keV, whereas M cell you can see very, very low. In case of tungsten and molybdenum, generally you use tungsten, so use molybdenum can be used X-ray tube. Also that from molybdenum you can use that K cell of rhodium, those have the electron binding energy are different in this case. So binding energy are unique to a given element. If you see tungsten, molybdenum, rhodium, the binding energy are different. The emitted X-ray have discrete energy that are characteristic of that element. Because of that, so the target material used in X-ray tube that include that tungsten used, molybdenum used, rhodium, they are mostly high Z material, because the binding energy is proportional to Z square. To use this high Z material to produce X-ray. As the energy of the incident electron increases above the threshold energy, the characteristic X-ray production will occur, and the percentage of X-ray characteristic increases if you increase that, this power, that was at 100 kilovolt or 80 or 100, so depending upon that, how much voltage you are applying the X-ray, that probability, percentage probability you can able to get. Mostly if you see, it's a characteristic X-rays are, it's specific to each element, and they have depends upon that particular binding energy of that element. Because of that, you can use them. You can use them. You can use them easily. You can say identify the material. See here that is K alpha and K beta. You can see here. This is the background radiation that I discussed. This is the Westerholm radiation. Because of that, you will see a background. So that the heat generation is produced that because of the deceleration of that electron, that the X-ray, so we will get a background. And these are the characteristics: K alpha 1, K alpha 2, K beta. So K alpha 1, K alpha 2, there are almost equal energy. So it's we need to separate them during X-ray study, and K beta also. So if you see, the variety of energy transition occurs from adjacent alpha and beta cells. So in addition, distant beta, mainly the continuum peak you will see the continuum at the spectrum. In that you will see within each cell there are discrete energy level which result in high energy splitting. That K alpha 1, that is, that L cell, it's a 2 2s and 2p. Because of that, you will able to see all those alpha and beta and characteristics X-ray other than those generated by KSL are unimportant. Only KSL is our most important. You can see here that you have both K alpha and K betas are there. Then K alpha, if you see the energy K alpha 2 and K beta. Generally in X-ray diffraction studies, that nickel filter, you use nickel filter. The nickel filter remove the K beta. The absorption coefficient of nickel is almost similar to that of K beta energy of copper. We use copper target, copper K alpha target we use. And that K beta, copper K beta energy is equivalent to the nickel absorption energy. So because of that, with nickel filter, you can easily absorb this K beta and we will get K alpha and K alpha 1 and 2 line. The ratio is generally 6:3:1, alpha to 1:2 to K beta. So once you K beta you separate, you will get a sharp peak. But still, that in X-ray you may get a sharp peak like this in that sometimes you may see there is a splitting on the top. That's because of K alpha 1 and K alpha 2. There is slightly mismatch energy that may be splitting at the top. So this K alpha 2 can be removed if you use a synchrotron X-ray source instead of conventional X-ray source. If you use a synchrotron X-ray source, the K alpha 2 can be emission. It depends upon the Z value, that because of mostly low X-ray characteristics. And if you see for molybdenum, we have a zirconium K alpha, copper, we have a nickel K alpha, and cobalt, we have a iron K alpha we use in this case. And but another phenomena is occur here, X-ray fluorescence. Some of the material that also fluoresces. Like for example, if you take copper source, that iron, chromium is here. That iron, in case of copper target, you can see if you have copper target, iron can give you fluorescence. Because of that, you might have seen if you take some people who are working on Fe3O4 material, you will see, your background is very high. With the peak, your background noise is very, very high because of this X-ray fluorescence is giving to the background effect. So that because some atom absorb incident X-ray and fluorescence then and give you X-ray, fluorescence characteristic. So you have to take, depending upon this, if you take a molybdenum source, or in case of iron sample, you will not see the fluorescence effect. So that is used. And okay. So in addition to that, X-ray fluorescence, I discussed already the Bremsstrahlung radiation. Yes.
Hello. Sir, what is the use of filters in X-ray productions?
What I'm not getting actually. What is
What
the?
is use of filters? You described in the filters.
Okay, regarding okay. Yeah, I'll explain you. See, when you go for a X-ray diffraction study, like if you will not use a filter, you will have a K alpha and K beta line. So what will happen that all your diffraction spectra will be splitted. Like for example, if your peak should be, instead of coming like this, it will come like some this type of, it will be splitted. The peak will be splitted. K alpha, K beta both will use for X-ray analysis. So in order to prevent this splitting,
Okay, sir. Okay, understand.
so you use that K beta, because see that K alpha line will give some characteristic spectrum and K beta will give. So K beta you have to separate out by using filter. That filter will be Z minus 1. That means if your copper is filter, Z minus 1, that 29, which is nickel is 28. So you have to use 28, that nickel as a filter. For example, for zirconia, you can use molybdenum. For molybdenum target, you have to use zirconia as a filter and so on. So that K beta can be separated. Okay, but still at the top you can get little bifurcation, that is K alpha 1 and K alpha 2, and that can be separated out if you do high energy synchrotron source X-ray. So K alpha 2 will be, it's being a synchrotron source, it is highly monochromatic, and because of that you will not get K alpha 2. Okay. So then this background radiation I have already discussed. So this, because of this background radiation, it will give you, strong noise to the characteristic X-ray pattern, that it mainly produce the kinetic energy when projected electron completely, it passes through this. If you see electron 1, electron 2, and electron 3, you can see here the impact will be maximum, that this electron 1 with the nucleus, that will be maximum. So because of that, depending upon how close to the nucleus, so what will happen, that will be some background radiation will come, and that will give you noise in the sample. So you can see here, this is your background radiation, and this can be also, background filtration can be done. So accordingly, you can get a very good image. So you can see the average X-ray energy is about 1/3 to 1/2 of the highest. So if you see the X-ray maximum energy is here. So if you use that background radiation, 10 to 90 continuous background radiation, if you use the energy of about 40 kV, so what will happen? You will get background will be less in that case. So depending upon that, you can choose your wavelength. So mostly we use the 30 kV, mostly used in X-ray X-ray diffraction study. So if you see the X-ray, so the X-rays are used in different purposes. That, for example, you can use X-ray in security purpose in airport and cargo. The scanning of the material used with the X-ray, because you can see the image through the X-ray penetration depending upon the density of the material. And you can also in the medical radiography by using fractures, all those things, damage. You can see the bone damage by medical purpose. But in analytical, in scientific purpose, we use X-ray in fluorescence spectroscopy, X-ray photoelectron spectroscopy, and X-ray diffraction spectroscopy. And X-ray fluorescence, you have two parts. One is wavelength dispersive spectroscopy, and there is energy dispersive spectroscopy. Whether your X-ray, your peak is you are differentiating based on wavelength or based on electron energy. So energy, the energy based EDS is wavelength WDS. So we will discuss all these techniques. That is, next class we will mainly discuss X-ray diffraction study with fundamental principle, and then how you can use for the structural analysis, and some interpretation examples I will discuss in the XRD. Then XPS, all those analytical technique we will discuss. So today, so far we discussed mainly the interaction of matter. So take home message is, how X-ray, neutron, electron, they interact with the matter. In case of X-ray, you have a pair production, you have a Compton effect, you have a elastic interaction, you have this photoelectric effect, you have a photo disintegration will be possible. In case of neutron, you have a neutron scattering and neutron diffraction. Being magnetic movement, that magnetic scattering can be possible. In case of electron, you have a polyelastic collision, inelastic collision. Because of that, you will be able to get secondary electron or backscatter electron. How secondary and backscatter electron used to be SEM, that you will study when you go for electron microscope, and how the transmitted one will be used for PM. And then in case of photoelectron produce XPS or OJ electron spectroscopy, that we'll discuss. So broadly, all the characteristics, if you see that all the characterization technique will depend on all this interaction. So this is the basic, like I give an introduction to the subject devices, discussing the interaction of this matter with this X-ray, photon, and electron and neutron. And next class we will discuss about the X-ray diffraction spectroscopy. If any question, you can raise here, or you can also mail me at kcbarik@brc, that I have given in the first slide, that kcbarik@barc.gov.in. So you can mail me there. You can stop here. There is no questions. So we'll see you on one day, the next class about X-ray diffraction technique.